Okay, so thank you very much to the organizers. I'm really happy to be there. So the focus in this talk will be on a model of which can be seen of a model of a piece of conductive material with microscopic inhomogeneity. So the microscopic inhomogeneity is modelized by small random resistances. So you equip the lattice ZD with IID random resistances, and we make an assumption of ellipticity on it. So this means that they are uniformly bounded away from 0 and infinity, here between 1 and lambda, say. The individual conductances is just the reciprocal values of the resistances. And you imagine your piece of material as a large box in DD. So let's take 0n to the d. And you wonder what is the effective resistance through the box. That is, what is the effective resistance through two opposite sides, let's say AN and ZN here. So the effective resistance can be defined as the minimum of the energy of a flow going from AN to ZN over all unit flows from AN to ZN. And what is a unit flow from AN to ZN? It is it is a function defined, a real function defined on the edges, antisymmetric. What goes through one edge is the opposite of what goes through the same edge in the other direction. And it satisfies the node law everywhere except at both sides. So, and what enters the network at AN is 1, and the net flow outside the network at ZN is 1.
AN is the left edge.
Yes, here AN is the left side.
From A to Z. A to Z. So, and they're identified with zero resistance.
Yes, here it's equivalent to say that they are the same voltage. They are identified as vertex. Okay. So when you see that model, the natural question for a probabilist is what is the asymptotic behavior when n goes to infinity of that kind of thing. So first, let us understand what is the order of this effective resistance. And to see this, first let us call the reciprocal value of the resistance, the effective resistance, the effective conductance through the box.
So the resistance on each edge is uniform between 1 and delta?
No, any distribution between 1 and lambda, but IID.
But you're not telling us what distribution?
No. And so the reciprocal value of the effective resistance also has a variational formula. It is the minimum of the energy, a kind of Dirichlet energy dissipated on the box. So the energy is just the conductance. The energy across an edge is the conductance times the voltage drop squared, and you minimize over functions which are now on the vertices, and which have the boundary conditions to be 0 on AN and 1 on ZN. Well, in fact, it's not completely coherent with the last slide. It would be better to say 1 on AN and 0 on ZN, but anyway. And the minimum is attained at a unique function, which is the unique harmonic function on the box everywhere except at side AN and ZN, and which satisfies the boundary condition.
What's the harmonic function?
So here harmonic function means that when you have the weights given by the conductances, it means that V is harmonic at X is equivalent, signifies that the sum over all edges starting from X of C of E times V of E minus minus V of E plus equals 0. It means that V is the mean at some point. It is the mean, but the weighted mean of its values on the neighbors, weighted by the conductance. So here it's harmonic everywhere except at the sides. So to understand the order of Cn, there is a very simple candidate to be a minimizer. Let us call it V home. It's just V home of x. It's just x1 over n. So this is equal to 0 on an and 1 on Zn. And in fact, it is the true minimizer when all conductances equal 1. And so you see that then this sum here equals is of order n to the d times 1 over n squared. So it's of order n to the d minus 2. Okay. And because of the variational formulation, you can compare Cn of any of resistances. If resistances are in 1 lambda, you can compare it to the homogeneous Cn. And so for any collection of resistances in 1 lambda, you have that the effective conductance is of order n to the d minus 2. So n to the d minus 2 should be the right order. And so the effective resistance is of order n to the 2 minus d. So there is a law of large number, which is known since the 80s, rigorously in this context due to Kozlov. And in fact, it is part of a much larger theory, which is called the homogenization theory, and which has been developed notably by Papanicolaou and Varadan, Zhikov, Kozlov, and Oleinik, and Kuhneman in a discrete setting. And it is much larger, notably because you can, in order to obtain the law of large number, you can only suppose that the resistances are ergodic, translation invariant and ergodic. Okay, so but let us stick to the case where the resistances are IRD in order to go a step further in the analysis of the asymptotic probabilistic behavior of the resistance, of the effective resistance, and let us try to understand the order of fluctuations of the effective resistance. So there was an upper bound in the 90s by Ver, which showed that the variance is at least, I mean, it translates like to this, but it was not stated. It was on the effective conductance, in fact, but anyway, it translates like to this. So it says that the variance is at least of the order of n to the 4 minus 3d. And just to understand, this lower bound is the lower bound that you would obtain if you supposed, here that this V was just V homogeneous. So if this effective conductance was only a sum of IID conductances, then the variance would translate on the effective resistance as n to the 4 minus 3d. More recently, there was a result by Gloria and Otto, which gave an optimal estimation for the variance, but not really for the effective resistance, but for something which is called the corrector, and which comes from homogenization theory, and which has the advantage to be translation invariant. But well, so it is not exactly what we want, but they had a good notion of a good result on the variance of something related to the effective resistance. And is there a central limit theorem then? We can wonder if Rn is asymptotically Gaussian once correctly normalized. And so we will address this question, and there are mainly two other results. One by Nolan, which gives the Gaussian approximation and some hypotheses, and another one by Biskup, Salvi, and Wolf, if I have some time, I will. I can maybe compare their results in the end of the talk. So the conjecture is as follows. The lower bound by there should be the right order. And once renormalized, the effective resistance should be approximately Gaussian. I don't know how to prove precisely this result. So the main result of the talk will be to show that it is true on the torus.
For d equals 1, it's
Sorry?
for d equals 1.
Yeah, for d equals 1, I know how to prove this. Okay. So in the first part, I will just forget the setting of the box and look at a general countable network with bounded degree and try to understand what we can say about the fluctuations of the effective resistance and maybe a Gaussian approximation on it. So G will be a countable, oriented, symmetric, and connected graph with bounded degree. The fact that, so it is symmetric, it's just for notational reasons, in fact. So
What does it mean symmetric?
So since it is oriented, it's just that I allow, in fact, both edges occur in both directions. Every edge occurs in both directions in E, but then I define E1/2 to be just one of the orientation, yes. Each edge occurs with one of them. And then I take some deterministic, for the moment, elliptic resistances on the edges. And I want to precise a bit the flow, what I call a flow. So I give a name to the energy. If theta is an antisymmetric function on the edges, I call ER of theta the energy dissipated on the network. And we call D star the boundary operator, which takes a flow or a function on the edges and gives a function on the vertices. D star theta at x is just the net flow going out at x. So we said that theta is a flow from U to V. Essentially, I already told the thing of intensity I, if in fact d star theta is 0 everywhere except at U and V and equals I at U and minus I at V. So this means that the node law is satisfied except at U and V. Now we need the notion of current. A flow I from U to V is a current if it satisfies. So in addition to being a flow, if it satisfies the cycle law, that is for every oriented cycle, EI, EN, the voltage drop along that cycle is 0. This is equivalent to say that one may write this is equivalent to the fact that I derive from a potential so that there exists some function V on the vertices so that R of E times I of V equals the voltage drop along a G. Yes, and a small remark is that the fact to be this thing, when I derive from a potential, the fact that V is harmonic at X is equivalent to the fact that I satisfies the node law at X. So now I recall the notation. The effective resistance between two vertices U and V is just the infimum of the energy dissipated by a flow theta over all unit flows theta from U to V. So the infimum is uniquely attained, even in this countable setting, because you are minimizing a Hilbert norm over a closed subset, and we shall call it I sub r to uv. So in fact it is a current, which is called the minimal unit current from U to V. So recall my two questions. What is the order of the variance, and can we say something of about a Gaussian approximation? And the
Order variance of what?
of the effective resistance.
But now U and V are arbitrary vertices?
U and V are arbitrary vertices, and in fact, I would like to understand if we can bound the variance of the effective resistance. Maybe
Well,
not.
why are you talking about the variance? You haven't even said what the expectation
I'm
is.
sorry. The resistances, they were deterministic, but now I will take them independent and random variables independent in one lambda, let's say. So this becomes a random variable.
No, okay, no, I understand, but I say I don't even understand how this resistance. I don't understand the first order. How it depends on the distance between U and V. And you're
Okay,
already talking
it
about
depends on the graph. I'm not saying that I will give a universal bound for any graph, but I want to understand mainly how does the effective resistance fluctuates. Okay, you will see later. In fact, what we will show, I can say it to you.
Once you know the first moment before the second moment.
Yes, but I don't know. The first moment is too dependent on the vector, on the graph. What I will show is that.
Raphaël, but the first moment, one should say, is not dependent on the randomness. So if you just take resistance as 1, you'll get some order of magnitude, and the fluctuations will not change, will only change. So the order you know of the resistance just by putting deterministic resistances. But the variance is a real mystery.
And so just another comment. So to match the variance lower bound from before we made the torus,
Okay.
it's possible a test function current could give the right order, because if you choose an appropriate flow, that gives an upper bound on the resistance.
On the resistance, but the variance is. It doesn't tell you something on the variance.
Yes, but for the lower bound, you said it was a test function for the conductance, for potential.
For the lower bound, but not on the variance. For the lower bound of the
okay.
of the effective resistance. So the strategy is to use the Walsh decomposition as introduced by Ahmed Atami in the first talk of this workshop. So I will recall briefly what I need from the Walsh decomposition. So let us take a square integrable function of the resistances, of the collection of the resistances. So I just suppose that the law, for the moment that the law of the resistances correspond to an independent collection of resistances. It is a product law. So the Walsh decomposition of F is to write it as a sum over all finite subsets S of the edges of F sub S, where F sub S are functions which depend only on the resistances inside the subset S. And they can be written as follows. If I call delta EF, the delta E is the following operator. It maps F to F minus its mean against coordinate E. It is a kind of discrete derivative. You can view it like this. But then Fs can be expressed as the conditional mean, given R sub S, of the product of the delta E for E in S applied to F. So here you should think of this as a partial derivative, essentially roughly a partial derivative with respect to all the resistances which are in S. Okay? So as we saw with Hamed in Hamed's talk, delta EF is the sum of Fs over all sets S which contain edge E. Okay, this is just because this, if you integrate this over an edge which does not belong to S, it just remains the same. And So this is, since this is an orthogonal projection, and f empty is just a constant, okay, since it depends on nothing, and it is necessarily the mean of f. And so if you want to compute the variance, you just have to compute the sum of the L2 norms squared of fs for an s not empty. This is, of course, always smaller than the sum over all sets S of the cardinal of S times the L2 norm of Fs squared. And this, just by using this formula and interchanging two sums, is the sum over all edges E of the L2 norm of delta EF squared. So this is, in this context, variance of F less than this, it might be called a Poincaré inequality. In fact, it is a Poincaré inequality. But this will be useful because the variance of f, we are looking to understand the variance of f notably, and this can be easily evaluated in terms of a mean of something which involves the optimal flow, the current, the minimal current. So what we will show is twofold. I'm sorry, what?
I have about half an hour.
Thank you. So what we will show is twofold. First, in fact, uniformly in U and V, and uniformly in the graph, it turned out that the Walsh decomposition is concentrated on low levels. The sum over S of the cardinal of S squared times this the weight of S, let's say, is upper bounded by the variance. This is the variance of F. Okay, so you see that, and here the constant only depends on lambda. I mean, maybe I should stress the fact that this is not true if we consider a quantity which which looks a bit like the effective resistance, which is the first passage time of first passage percolation. If I call TUV the infimum over all flows from U to V of the sum over E of R of E times the absolute value. So I put 1 instead of 2. Then this is the first passage time from U to V. And we know that this is not true. This is not true because on ZD, this cannot be true because on ZD we know that the variance, in fact, on ZD for first passage percolation, we know that this quantity is larger than the variance of, is large with respect to the variance of V. Because we have a lower bound of the variance which is of the order of distance from U to V over log of the distance, and this is essentially of the order of the distance from U to V. So putting a square here changes completely the behavior of the Walsh decomposition, but it is not really surprising because in the Walsh, when you are looking at the flows, the optimal flow can change very smoothly, whereas the path cannot change really smooth. Well, no, maybe it's not convincing. Sorry. Okay, so we will show this. F now is the effective resistance. And we will show another thing which is important for Gaussian approximation. We will show that the L2 norm of F spent on sets of large diameter can be controlled by the variance of F times some coefficient here, which can be written like this. So to understand, IRE is the optimal current from E minus to E plus. So you take every edge E in the graph. You wonder, you look at the optimal current from E minus to E plus, so it is a current in the graph. You look at a box, a ball of size of radius L of around E, and you wonder what is the energy dissipated by the optimal current from E minus to E plus on that ball. So it is natural, for instance, it is true in ZD, to believe that when the L goes to infinity, this will go to 0. But so this bond will be good if this can be true uniformly in E and R. So what will be the consequences? One, the first inequality will give us that the variance is in fact of the same order of the upper bound of the Poincaré inequality, which is essentially of the mean of the sum of IR 4 of V. So this is this. So you asked what kind of bond on the variance we have. So I obtain this. It doesn't tell me what is the order of this, okay? But so we will look at this later. And the second thing is that if I can prove that alpha L is small, then on a graph with bounded degree, the sum of Fs of S of small diameter is a sum of locally dependent random variables. And then F will be approximated by some, can be well approximated by a normal, a Gaussian random variable under Lindeberg type condition. So just for these two results, in fact, one can replace the ellipticity condition by a condition on the moments on RV and COV. But afterwards, I will need stronger. I will really need the ellipticity hypothesis. So I will prove. I will show you how to prove 1 and 2. So the idea is the same for both inequalities. We need to bound the L2 norm of delta E prime F squared. So recall that delta E prime is a kind of second partial derivative with respect to R of E, R of E prime. So let us look at, and F is the effective resistance. Let us look at the first derivative. So this is easy to see that it is the sum. The first derivative, the partial derivative with respect to R of E equals the value of the optimal flow at E squared. If we want to differentiate twice, so we differentiate this optimal flow at E with respect to another resistance, and this makes appear the optimal flow at E prime times IR E prime of E over R of E prime. I recall you that this is the optimal flow from E prime minus to E plus. So we have a formula for the second derivative, okay? And because partial derivatives can be done in both order, then you see that what we obtain here is necessarily equal to this, just by exchanging the roles of E prime and E. And in fact, the fact that this quantity here equals this quantity here is known. It is called the reciprocity law in the electrical network theory. So the first remark is that this equality explains why I say that the upper bound of the Poincaré inequality is of the order of the sum over E of the mean of IS to the 4 of E. Okay? So just because this is essentially this partial derivative. And to understand this, just to explain how we obtain this, it is, maybe I will do it a bit quickly. Just, in fact, you start from the node and cycle laws. Suppose that you are on a finite graph. Then I is characterized by the node and cycle law. And so you differentiate the node law. This tells you that partial IRs with respect to RV prime is in fact a sourceless flow. And you differentiate the node law, the cycle law, sorry, and this makes appear an additional term when one of these edges is the edge with respect to which you are differentiating. But anyway, using this, in fact, you recover other cycle laws and node laws for essentially the partial derivative of the flow. And the intensity is given by this. The intensity is IRV prime over RV prime, and you see that there is uniquely a voltage drop along the edge across which you are derivating, with respect to which you are derivating. So this explains the appearance of of this factor here. So now suppose that, well, maybe I should recall you what is one. So one was this. We want to prove that the L2 in the Walsh system, the second moment of the cardinal of S is is bounded. So first, I use the formula for the second partial derivative of f. So this tells me this. We want to sum over all couples E prime, which are different, where E is different from E prime. So I want to separate these two terms. I just use 2ab less than a squared plus b squared, a very important inequality. And here, in these two sums are completely symmetric. So I just have to care about one. Okay? Here, in fact, I use the fact that I use the reciprocity law. So I obtain, I just have to care about this term. Since this does not depend on E prime, I obtain this. And this, if I put the resistance of E prime in front of this term, I exactly obtain the energy dissipated by the unit flow from E minus to E plus. And this is the effective resistance, if I sum over all edges E prime, this is the effective resistance between E minus and E plus over the whole network. But it is always less than the resistance between E minus and E plus. I always can take a flow which goes stupidly from E minus to E plus by thinking 1 on this edge and 0 elsewhere. So this is upper bounded, and this only depends on lambda. So I obtain this result, and we already saw that this is of the same order of the upper bound in the Poincaré inequality, the Dirichlet energy here. And so what we obtained here, when we interchange the sums with the fact delta E prime F cancels all Fs for S we do not contain E or do not contain E prime. So this is essentially this. In fact, it's the sum over S of cardinal of S times cardinal of S minus 1 times this. So we obtain an upper bound of the second moment by the first moment of the cardinal of S in the Walsh space. And this can be obviously this implies obviously the kind of thing. Notably, there is noise stability in the title of my talk. Notably, this shows that the effective resistance is always noise stable in the sense of Benjamin, Nicolai, and Schramm. Uniformly noise stable, uniformly in U and V, and in the graphs. The proof of two is essentially the same. In fact, the only point to notice first is that if I want to upper bound the sum of the diameter of S, the sum of the L2 norm of Fs squared over sets S which have large diameter, larger than L, I can upper bound this by this sum, the sum over all couple E prime, which are distance at least I, L, of the sum over all sets S which contains at least E and E prime of the L2 norms, the Walsh norms. Because when a set S has diameter larger than L, you can find a couple of edges, E and E prime, belonging to S, which are at distance at least L, larger than L. So, and this equals this, and you do the same trick as before. And so the only thing to notice is that the sum that you are doing here is really symmetric in E and E prime, so that you can do the same trick as before. And what appears then, if I split this sum in two, the sum over E and the sum over all edges E prime which are far away from E, I just upper bound then the sum over E prime by all possible values over E and over all resistances, I get the second inequality. Okay, so I will. Well, maybe I will go a bit faster on this. Just to understand where the Lindeberg conditions intervene, if I call now R bar the normalized effective resistance, and I want to throw out all Fs which are for S which have large diameter. So I define J of L the sets S which have diameter less than L and which are non-empty. There is a mistake here. There should not be an L2 norm here. So it's just the sum of Fs over those sets S which count. And RL bar its normalization. So there is a result by Chen and Shao, for instance. There are other results, but the one by Chen and Shao are really good, and which bound the L infinity norm between the PDF of the normalized Gaussian, the standard Gaussian, and the PDF of RL by a constant which will depend only on L and times something which is the sum of the L3 norm of Fs23 divided by the standard deviation of RL to 1/2, to 3. Sorry. So the point is that if these quantities are well spread out, this will be small. Okay, so this is where the Lindeberg type condition comes from. And it turns out that you can relate these quantities when S is of bounded cardinality. You can relate these quantities to...
S is bounded diameter?
S has, here in J of L, S has bounded diameter. But if S... It suffices to have S of bounded cardinality to relate, to upper bound this norm by a norm which is easier to compute, which is the projection of F on only the Walsh subspace induced by the set, the singleton E. And this is upper bounded by here, Fe, okay, it's on the first level of the Walsh system. On the first level, almost nothing moves. You only, Fe only depends on R of E. So there is very little variance here. And, okay, so this is upper bounded by this. So what we obtain is an upper bound of this kind. And so if you can show that this is really small, then you will have a Gaussian approximation for RL. And on the other hand, if you can show that alpha L is small, then you know that the original R bar is close to R, to the one where we only kept the small diameter sets. So to summarize, there are two conditions for Gaussian approximation: alpha of L small and the Lindeberg type condition. So
About 10 minutes.
Yes, 10 minutes. Okay. So I wanted. So this slide is just to say that why I cannot adapt this setting to the box. In fact, so the optimal flow on the box, it corresponds to a voltage which is constant on which has the additional. No, sorry, excuse me. IRE is. It was it was the optimal flow on the graph, on the countable graph, between E minus and E plus. So there is an analog in the box when we differentiate the effective resistance on the box and so on, which would be a voltage, but with the additional condition that it is constant on AN and on ZN. So either you consider AN and ZN as single vertices, and then this will be really harmonic, but we will not have a bounded degree graph, and so everything breaks down. Either you don't consider AN and ZN as single vertices, but then VRE is not necessarily harmonic on the whole box outside E minus and E plus. So there is a problem here, and I will skip. Essentially, I do not exactly know how to prove. I only know how to show, for instance, that the analog of alpha of L will be small, but only uniformly over edges which are far away from the boundary, and we have a problem at the boundary. Okay. A more important remark, maybe. Since I was on a general graph, I did not make any assumption on the or translation invariance. It doesn't have any sense. So, my resistances were just supposed to be independent, not necessarily IID. In fact, on the box, if we only suppose that the resistances are independent, it is not necessarily true that we have Gaussian approximation. And this is due to the fact that we can arrange elliptic resistances in a way that attracts some part of the flow to which is it will not be a positive fraction of the flow, but it will be too large, and it will have the effect that it will have the following effect. In fact, you put edges like this which have small resistance, okay, and then the edges in green have large resistance, and again small resistance, large resistance. Okay, this will attract a part of the flow here, and what will be true on that kind of network is that here the voltage will behave. Suppose that we center this around the origin. The voltage will behave like x over n to some power. let's say eta will depend on the difference between on the quotient between the resistances in blue and the resistances in green. And what will be true is that the absolute value which goes from an edge, the central edge, let's say, E, will be of the same order as the whole L4 norm, L4 norm to the 4. So this is the order of the variance. And so a positive part of the variance is owned by this edge here. And so if you have for instance, Bernoulli resistances, you will still see in your fluctuations that that kind of Bernoulli behavior.
Raphaël? Okay. Is the same true if you just fix all edges to 1 constantly, then just take 1 to be Bernoulli?
All edges, the edges, the green edges are large and the blue edges are small.
So what happens if I just fix all of them to 1?
All edges to 1 and 1 edge Bernoulli? No, it will. Everything will be fine.
So what is fine? What are you proving?
This is here. I do not prove anything. I say that. I said that, and in fact, I do not have a full proof of this. But it's there is a continuous, well-known counterexample in the setting of harmonic analysis, which shows that you can have a harmonic voltage which will have this behavior. And the behavior is that the flow going through the central edge here to the 4 has the same order of the sum over all edges of IR4 to the 4.
But the Gaussian approximation clearly does not always hold. I mean, this is...
Does not?
What you're showing in the Gaussian approximation does not hold.
How I deduce that this will not imply... Because, I mean, if... The influence of an edge is of this order. The influence of edge E is of this order. And when I move the resistance across edge E by a constant factor, it will have an impact on the fluctuations, which will be of the order of the typical fluctuations. So if it would be a miracle to have exactly the good shape of random variables, which will do that it will still stay Gaussian.
But in my example, you also have fluctuations of the order of the typical fluctuations.
No, because if everything is 1 outside, and here you just have a 1 Bernoulli random variable, the optimal flow will just throw a very small portion of 1 through your edge. It will throw 1 over n to the d minus 1 through your edge, essentially. This is not true here. Okay, I think... so, I just have 0 minutes to talk about the torus. So, let us do quickly... I will only stress the main differences. So, if we have invariance, translation invariance, everything will become simpler. So we take the torus with IID resistances, and we take a cut, E0, okay, and a vertical cut here, and we define the effective resistance of the torus as the minimum energy of a flow which is sourceless over all sourceless flows. I mean, d star theta equals 0 everywhere. But we impose to the flow to have a net flow through E0, which is 1. So in a sense, for instance, this is satisfied by a path which goes through the hole, okay, like this. So in a sense, we force the optimal flow to go through to go through the hole, to go around the hole. Then essentially, the basic theory remains that there is a unique minimum, and the minimum is uniquely attained, and the resistance is of the same order as before. And here we can show the theorem. I will only explain one thing, just very quickly. So the analog of alpha L before is this kind of thing. I want uniformly in N to have some kind of energy dissipated which goes to 0. And the main thing is the following. So because of translation invariance, you only have to focus on one fixed edge, and so that this is true. And seen from a fixed edge, the torus converges to ZD. Okay? In sense. And here, thanks to uniqueness of currents and to this convergence of ZD of the torus to ZD, you can show that what played the analog of the partial derivatives of the second partial derivative of the flow on the grid on the general on the box. Here it will converge to the optimal flow from E minus to E plus on ZD. Okay, so and next there is a compactness argument which allows to show that this is true. But the main point here, which makes everything work, is the uniqueness of currents on ZD. Well, I will stop there.
Can you do something on the cylinder, some in-between model between the torus and the box?
I don't think so. I'm not sure. In the end of the talk, I wanted to say that in fact, so there is this article by Biskup, Salvi, and Wolf, which is really nice. But so one important drawback is that they only work with small ellipticity contrast. That is, they require that lambda is close enough to 1, which in fact changes many things due to some theory of harmonic analysis. But so they announce a result without this condition. So this would be very, very, very nice. Okay, but they use a lot of homogenization theory. They use part of homogenization theory, and one motivation of what I did was to obtain result without too much hypothesis of translation invariance and so on. So the first part is that. But so on cylinder, I don't think I can do something.
Somehow, a related question is sometimes you can approximate the function on the box by some sufficient symmetric function.
Yes, and that is what Biskup, Salvi, and Wolf do in fact. Homogenization tells you that you can approximate, in fact, the voltage on the box by translation, by in fact a stationary version of the voltage, but the problem is that to obtain something at the level of the Gaussian approximation, you need the approximation to be very strong, to be in L4 in a sense, because of this order of the fluctuation. And for this, they require for the moment the small ellipticity contrast.
Do you know how specific some of these results are to the effective resistance? I mean, if I give you some other optimization program on variables, is it a more general understanding of what makes central limit theorem hold here? Or? Or it's very unique, very
Well,
specific?
no. Well, I think that probably there is a way to generalize part of it. But well, first there is this counterexample here, which shows that you need some convexity in your optimization, strict convexity. But if at the beginning we only differentiate twice and bound the second, in fact, partial derivatives by some product of the first partial derivatives times something which goes to zero. In fact, this is essentially what is important, and this could be generalized in a number of settings, maybe. In fact, and in this, a hint for this is that the no-length result uses an inequality by Chatterjee, which is what he calls the second order Poincaré inequality. And so in this context, maybe we should understand, because Chatterjee used his second order Poincaré inequality for other optimization, for other approximation in optimization setting. So maybe it can be that.
Other questions? Let's think of it again.